if you increase the diameter like to 1 mm or 1 centimeter, you have to consider a more refined mesh. So let's now click on apply to save the setting. It's too slow today. Come to the phase interactions. I am using the most common rack coefficient mathematical model, and there is only one mathematical model for the slip velocity. Also for the surface tension we have the value of it's not okay, it's the same as it we use for the air and water, 0.072 Newton meters per meter. And here in the heat and mass reaction we have to define the mechanism of evaporation, cavitation. So I am using the Zwart-Gerber Elmery model for the cavitation with the default values. You can also define the evaporation and condensation from here. So click on apply. Close. Come to the boundary conditions. Axis is already defined as axis. Change the velocity inlet to pressure inlet. Write down the value 256, and the initial stage there is only water and no water vapor. Also for the outlet, the pressure is 95,000. Click on apply. And close. Come to the methods, keep it simple, and then come to the controls. So make it 0.1 for the pressure and 0.1 for the momentum, so it can be easily converged. So high the number, more iteration for this convergence, but it definitely the solution will be better. But we need, if I write the number 1 for momentum, so I have to use more refined meshing and more number of iterations, so I can converge the solution. So in this case I am using small values. Come to initialize and click on inlet and click on initialize, and then come to the iterations. I am using 2500 iterations, so I am not going to run it again to save the time. I have already run it. So those are not shown here because I had closed the file. So let's come to the post processing after running the simulation. Take a plane in XY, click on apply. Now take a contour and plane 1, and we will see the pressure. Let's increase the length of the legend so numbers are easily. Okay, so to mirror the section, first of all we will duplicate the contour 1, click on OK, and let's go to the mirror 1 and apply, and apply rotation in ZX plane. So stop it here and change the location. So now it's okay. Also, if we hide the wireframe, so now we have a smooth contour. So in this way we can see the full section. Also, now let's check the velocity. Click on apply, and also for this second contour click on velocity and apply. So we can see the stagnation zones are here, if you can see my cursor, and the velocity is low near the wall in the nozzle. So if we see the cavitation, vapor volume fraction, so the cavitation occur where the velocity is low. So you can see it, the cavitation is directly related to the velocity. So the cavitation is being occurred where the stagnation zones are there. So that's all. Now is there any question to regarding this simulation, you can ask in the comment section. I will answer. Yes, the torque that is obtained from the experimental results definitely can be verified if you use the appropriate conditions. But what I have told you, for the MRF approach in Ansys Fluent, you have to use very less time step size and a very refined meshing. Also, if the boundary of meshing of the rotating zone and the static zone are not overlapping appropriately, it will also cause the error will sorry it will also cause the error in the simulation. So if you want to if you do not have the restriction, I recommend you to use the CFX instead of Fluent, because it is specially designed for the turbo machinery. So I think there is no question regarding the cavitation. So let's come to the second problem. Which is the oil water mixing in pipe. My system is working really slowly. I think it is happening due to low storage. Okay, it's open. So let's import the geometry. Okay, so the process of meshing is very tricky. We cannot define the any any of the single method for the meshing. Like if we see the element quality, it's very good now. The minimum element quality is 0.6, and if we see the aspect ratio, it's also very good. But the meshing is not good because we have only a small number of steps which will that will not give us the real that will not give us the real representation of the problem. So first of all, I am going to add the sizing of let me take a bigger number of so we can see it faster time. I am not opening two analysis systems. This is the same analysis A, but I have already done it. So now I am demonstrating the same simulation to you. So to save our time, I have already run a simulation. That's why I am using the two analysis systems. It's taking time. Let me give it more. So my system is accidentally performing slowly, otherwise this kind of meshing is done on the latest versions. Like if you are using i5 with HQ processor or H processor in 8th generation or 10th or any latest generation, this kind of meshing can be done within 10 to 15 seconds. So if we see the meshing, now the element quality, it is 0.96, and aspect ratio, it is also fine. But again, we have to make these decisions. Like I want to see the better results near the wall, so I will add the inflation layer. So one inflation layer I will add here. Number of inflation layers 5, and I will add one inflation layer. This wall, and we'll choose the number of inflation layer to 5. The aspect ratio is basically, if we google it, so it's the deformation of the cell. Like if you see, it is the perfect box, but if we make take this edge and try to deform it in the shape of like the parallelogram, so it is not a box more, like it is not an ideal hexagon, it does not have hexagonal shape. So this is what we call aspect ratio. The ideal aspect ratio for any analysis, it should not go so you can ideal aspect I was talking about the aspect ratio. The ideal aspect ratio is up to 8 or 9, or sometime 12 or 13 is fine. And element quality, the best element quality should be more than 0.1. If the element quality is below 0.1, you will not get the better results for the simulation. So let us define the boundaries. This is the inlet water, oil inlet, and outlet. Update this meshing. Start the Ansys Fluent to define the physical models. No, we use the processor cores, not threads. So if we see the problem, here is the water inlet and here is the oil inlet, and both of the fluids are immiscible, so we can use the free surface to have a distinguished boundary between the oil and water. So in this simulation I am going to use a transient or time based simulation. We will also have the impact of gravity in the y direction. So define it to minus 9.81. So comes to the material first. Oil is not available in the database of the Fluent fluids, so we will take the water liquid from here. With the default conditions and change the properties of the air to the oil. So if we see the properties, 820 is the density and 0.035 is the viscosity. Click on yes. Now go back to the models. In this case we are using volume of fluids. We have sharp interface. Click on apply. Primary phase is water, and the secondary phase is the oil. So click on apply. Come to the phase interaction. So you can see here in the VOF there is no drag, lift, slip velocity mathematical model available here. Only surface tension coefficient model is here. So surface tension is 0.035 Newton per meter. Click on apply. Come to the turbulence model. Remain it to the default K omega SST model. Come to the boundary conditions. Define the velocities. The speed of water is 0.325. And check the oil volume fraction. it is 0 for the water inlet. Go to the oil and let the velocity at the inlet is 0.175. Click on apply and go to the oil volume fraction. There is a software works, so click on oil inlet again and go to the oil phase. Volume fraction for oil inlet is 1. Click on apply. So now come to method, use piezo. Second order implicit. Sorry, we are using the explicit, so it is not available for that. Second order implicit is only available for the implicit models. So come to initialize from all zone. The oil volume fraction at start is 0. Now you want to create the animation, so to create animation, come to the contour, new, make like I want to make the face contour volume fraction of oil, so I have built this. Now go to solution animation, take the entity you want to animate. I'm using in memory, so once the Fluent will be closed, I can't see this animation again. I cannot see this, so I'm using after every 10 time steps. So click on OK. If you want to make the or visualize the results in the post processing, so you have to go to the auto save. So I am taking 10 time steps. So after every time 10 time steps, my solution will be saved and I can create the animation in the CFD post. So for the time advancement, I am using the adaptive. So in adaptive, this software will determine the best time step size to get the converged results, but I have to define the minimum time step size and the maximum time step size. So for this solution I have taken the same value, and the maximum is the 10 second. So global current number, the larger the current number value, the advancement of the time step size will be larger, and lower the current number, so advancement of the time step size will be lower. So number of iterations 30. So click on calculate. I have already calculated the results, and created the animation images from the results. So you can see the interaction of the oil with the water. So you can see the oil has a clear and distinguished interface with the water. If you see here, here is a clear distinct interface with the water. So you can see the solution is converged in the first time steps. So we will get the better results for the simulation, and for each time step size it is taking the physical time by itself to get the best convergence results. So that's all for today. After the simulation has been completed, you can create the animation